Yeah, oh yeah, I do want to record. So let me back up. Chapter 5, Exam 3. This is our review session for the exam, which nominally is next Tuesday. Okay, so for number 1, we want to know what characterizes a gas. Well, the specific problem, the answer to that one is just low density. What does that mean? Density is mass per unit volume. So that means for a given volume, you've got very little mass. And that sounds silly, but it's nonetheless important to recognize, because in order to be low density, there have to be few atoms or molecules in the gas and lots of space between them, which is also characteristic of gases. All right. So let's define what is pressure. Pressure is a force per unit area. And that, let's see, who we got? Jeannie. Yeah, okay. All right. Now, we can think of various types of units of measure for that one. And by the way, the answer for that one is D. Force per unit area could be newtons per square meter. Newton is a unit of force. And if we say that, then that's in SI units. And it's also given another value, which is equal to the Pascal. All right, and that answers number 3. The SI unit of pressure is the Pascal. Now it's nice to assign persons' names to values like this, like the Newton or like the Pascal. But when you start doing dimensional analysis and you need to cancel units, you've got to know what that means. Because if you have pressure in a calculation and there's no other unit in there to cancel pressure, then you got to keep it, unless you understand what the Pascal means, newtons per meter squared. Then if you're in a calculation and say Pascal is in the numerator, which would make it like that, but you have another unit that's in there that's newtons in the denominator, then they cancel. But if you have only Pascals, then you can't cancel them. So that's why you need to understand what the Pascal means, or what, in fact, what the Newton means, right? I went through that before. The Newton is derived from Newton's second law of motion. And if Newton is the force, then we have mass in kilograms and acceleration in meters per second. So kilogram meter per second is a Newton, in case you need to cancel something where Newton is part of the calculation. Okay, so that takes us through number 3. Now, if we did something like number 4, where the question is, which one represents the greatest pressure? And they're all different units, right? So you can't do a direct comparison because you can't compare apples and oranges, as they say. So you have to convert each one of these to some common unit. So this one is atmospheres. And this one is 517 millimeters of mercury. And this one is PSI. This one is pascals. And this one is inches of mercury. Okay, so we can convert, but pick any one. I would pick one that we already have, then you don't have to convert 4 of them, rather than pick one that's not up here. So my choice would be atmospheres. Just leave that one alone and convert the rest of them to atmospheres. So this one would be converted by 760 millimeters of mercury on the bottom, so it would cancel that one. What does that equal to? That's 1 atmosphere. Then you do the calculation. How about PSI? 1 atmosphere is
14.7.
14, I think sometimes they say 6.9. 14.7 is good enough because you only have 3 significant figures there anyway. Pascals. I don't have that one memorized. I'm pretty sure it's in your useful information. So over here on the left, yeah, 1 atmosphere is 101.325. 101.325 pascals per atmosphere. Okay? And then inches of mercury, I do remember that one. Inches of mercury is 2992, 1 atmosphere. And then you would just do those calculations and compare, see which one is bigger. In the interest of time, I'm not going to do the calculations, but it should be this one right here. Should be the greatest. Okay? So this would be very time consuming, obviously. It's really a test of unit conversions. Okay, how about 5? We'll just round off page 1. Okay, a glass column is filled with mercury and inverted in a pool of mercury. So we got, sometimes it helps to draw a picture. So we have a pool of mercury here, right? Convex meniscus. And then we have a column filled with mercury and inverted. Okay, so we have a column here. And I assume it has to be closed at one end, otherwise you can't fill it up, right? So it's filled with mercury, inverted in there. The mercury column stabilizes as at a height of 729 millimeters above the pool. So the distance here, just say something like that, is 729 millimeters. What's the pressure of the atmosphere? Oh, that's another unit conversion, isn't it? Right. 1 atmosphere. Okay, so those cancel. And it's going to be less than 1 atmosphere. Right. So you know A can't be right because that's bigger than this one. And D can't be right. So it's either B, C, or E. And when you calculate it, of course, it should come out to be. Well, you could probably even estimate that one. Because B is 3/4. And this is greater than 3/4 of that. It's greater than 2/3 of that also. So you wouldn't even have to do the calculation. Just process of elimination gives you the answer C without a calculator. If you are proficient in estimating, and that's a very good skill to develop, estimating values through calculation. Okay. So on page 2, and let's see which one I've got marked. 6. Okay. Well, actually 6. Okay, we'll do it. It's another unit conversion. The local weather forecast reports a barometric pressure of 30.4 inches of mercury. So we just need to convert 29.92. Okay, so it'll be just a little bit less than 30.4. It's not 1 atmosphere. It's a little over an atmosphere. It's not 900 atmospheres. It's not 4 atmospheres. It's not 10 atmospheres. So you can do that one by estimating also as A. Okay. Let's see. I was going to do 8, but it's just another conversion of PSI using 14.7 or 14.69 as your conversion factor to atmospheres. Then I marked off the statements on each of the gas laws. Number 9 is Boyle's law. Which one of these statements best represents Boyle's law? You can read through each one of them, but I think it's best to go from the formula and then see which one of these fits the formula. So pressure times volume is a constant. So that means pressure is inversely proportional to volume. And let's see. The volume of a fixed amount of gas is inversely proportional to its pressure. That's B. While we're on the gas laws, let's see. Let me skip 10. I want to go to 11. Let's take them in the order that we studied them. Charles' law. What's Charles' law? What does it relate? Volume and temperature. So they're directly proportional. So if we look at our choices, the volume of a fixed amount of gas is directly proportional to its temperature in Kelvin at constant pressure. So that's C. Okay. Then I go back to 10. This is Avogadro. So Avogadro's law relates what? It relates volume and moles. So the one that fits that is, let's see, which one has volume and moles in it? looks like A. Equal amounts of gas. When they say amounts, they mean moles. Same amount means the same number of particles. Equal amounts of gases occupy the same volume at constant temperature and pressure. Now that is not obvious from this one. You have to do some derivation. But when I described Avogadro's application, where we had equal volume containers, and then if of course the volumes are the same, the pressure is the same, the temperature is the same, then the moles have to be the same. If all of these other three are equal, then the moles of each container has to be equal. And that's what A says. Okay, let's see. We have another law. We'll just get all the gas laws out of the way. And this one's number 96. Which one haven't we done yet? Actually, there are two of them we haven't done yet. Still on, yeah, I'm still in frame. There we go. Dalton's law. Actually, we don't stop there. Dalton's law of partial pressures. I think Dalton's got another law that we studied already. Definite proportions, I think. Okay, so Dalton's law is what? Well, it says the total pressure of a confined gas, of course, equals the sum of the pressures, the individual pressures, we call partial pressures, of each of the other gases that are part of the mixture. And it goes on out to however many you have. So it looks like total pressure mixture of gases is the sum of the partial pressures of all the gaseous, I should have said, instead of compounds, gaseous components. That's Dalton's law. Let's see. Do I have Graham's law marked off? Here it is. 111. This is the other law that we had studied, Graham's law. So what does Graham's law say? Well, in words, it says that the rate of effusion of any gas is inversely proportional to its molar mass. So that means the lighter the gas, the molar mass of the gas, the faster it moves. And what we've got is an expression where we use mu as the velocity is equal to the square root of 3 RT over the molar mass. And I abbreviate that MW for molecular weight. So that means if we were to bring that molecular weight over on the other side and set this as our constant, then we would have a product of two variables, the velocity and the molecular weight. So as the velocity goes up, the molecular weight has to go down, and vice versa. So if you had two gases like, let's take noble gases. If you had helium, which has a molar mass of around 4, and we compared it to argon, which has a molar mass of 40. So which one would move faster at a given temperature? The helium, of course, because it's smaller. And by the way, why is that? Because the temperature represents the average kinetic energy of the molecules in the container. So if we hold the temperature constant, then the kinetic energy has to be the same for both gases. Right? For helium at around 4 and argon at around 40, and based on the kinetic energy formula, 1/2 equals mv squared. If you're just talking about individual particles, and they got to have the same kinetic energy, then for the lighter one, this mass and velocity are inversely proportional. So if the masses of one is greater than the other one, then the velocity has to go down. If one goes up, the other has to go down in order to have the same kinetic energy. So that's why Graham's law works. And of course, this is the expression of Graham's law, and it's in useful information in the back of your, it's in the back of your review document. It'll be in the back of the exam also. Oh, I didn't answer that question. So that would be E. The rate of diffusion of gases is inversely proportional to the square root of their molar mass. And that's true. Okay? Okay, so let's go back. I wanted to get all those gas laws done in a group. So let's go back where we left off, Charles' law. And let's see. What if, let's check. Okay, the next one I have checked is number 15. Gaseous chlorine is held in 2 separate containers at identical temperatures and pressures. And then it gives us the volume of each container. So you have 2 separate containers, and let's go down to the volume. Container 1 is 1.30 liters. So there's container 1 is 1.30 liters, and container 2, it also tells how many moles we have in here. So we have 6.70 moles. 6.70 moles. And then container 2 is 2.33 liters, so it's bigger. And the question is, how many moles does that have? And they each contain chlorine gas. Okay, that's all the information that we're given. Now, if we're going to solve for moles, what kind of problem is this? Is this a state function or a before and after? Well, actually, it doesn't matter the chlorine. It could be any gas. In fact, this one could be a different gas than that one. Doesn't matter. That's the way ideal gases behave. So the problem statement that chlorine gas is in both of them is irrelevant. It's blue smoke, as I call it, just to kind of fog your vision to see if you can really figure out what the problem is about. Okay, so we've got before, and this could be considered after, since Avogadro says that these two containers, because this is volume and moles, right? Volume and moles, that's the relationship, Avogadro. So we want to solve for this one. If this one's 1, there's our 1s, 2, there's our 2s. So that's the unknown right there. So we would plug in this value, 1.30 liters, and 6.70 moles. This one would be 2.33 liters, and this would be our unknown. And we just solve for that unknown. So if we bring this one over here, and that one goes over there, and this one goes over here, so 6.7 times 2.33 is 15.61, and then we divide by 1.3 because it came over here as that one went over here. And I get 12.0. Yeah, 3 significant figures, 12.0. Let's see. Is that the right answer? That's the one that's in the key. A. Moles. Okay? So, I don't know about you, but it always helps me to draw pictures. Or at least slap things up here in their proper relationship to one another. So I would put V1, N1, V2, N2, and write in the numbers before I tried to solve the problem. Okay, that was 15. And let's see, I better move it along here. I want to try I want to try 18. Okay, so 18 says body temperature is, and they already converted for you, 309 Kelvin. Right? Let's see if that's right. What is body temperature in Celsius, centigrade? 37. Centigrade. So if we add that, we should get, let's see, 0. Well, they're close. They said 309, so we'll take their number. So we got 309 K is our temperature. One of the temperatures, because it looks like there's another one in here. On a cold day, what volume of air at 276 K? 276 K. So this is the body temperature, and this is the air temperature. Must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? So where does this one belong? If we've got volume, where does 2.2 liters belong? What volume of air at 276 must a person with a lung capacity of 2.2 liters? So what temperature is the lung capacity? It's that temperature. That's the lung capacity temperature. 2.2 liters. Now we've got everything in its proper place, and we solve for that one. So this is Charles' law before and after. Right. So if we solve for V2, we start off with V1 over T1 equals V2 over T2. and we're solving for this one, that means that one just needs to come over here, right there. Okay, so V2 is equal to T2 times V1 divided by T1. Okay. So I get, let's see, two significant figures. That's 1.9 or 2.0, 1.965 liters. Let's see how it's presented here. Okay, they rounded it off to 3. B. So in test taking technique, you go for the best answer. I mean, even if it's not correct significant figures. Or did I put the wrong number? No, 2.2. So it should have been rounded off to 2, shouldn't it? 2.0. But the nearest one to 2.0 is 1.97. Should redo the problem to put a 0 in there. Okay, that was 18. Let's go to 20. Oh, is there somebody waiting to come in? Let Cody in. It's already been here. It must have got kicked off. Let's see, am I missing anybody else? Let's see, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I didn't include 1. Let's see.
It kicked me off for a second, but I just got back on.
Okay, okay. My count says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's right. Okay, because I'm number 11. All right. So let's carry on with number 20. The reason I picked number 20 is the solution that I give you in my handwritten worked out problems for this one is solely math based. And what I want to show you is that you can logically arrive at the correct conclusion without having to go through all that math manipulation. Because that's I know sometimes math can get really convoluted, to say the least. So let's read the problem. You're holding 2 balloons, an orange balloon and a blue balloon. Let's see. Before I draw the picture, let's look at what's the size. Let's see. The orange balloon is twice the volume of the blue. Okay, so the orange balloon, put it over here, is twice the size of the blue balloon. Okay. Now, what do we have in each one? The orange balloon has neon in it. And the blue has argon. All right. The orange balloon has twice the volume of the blue. We got that. Which of the following best represents the mass ratio of neon to argon? So we're looking for this. Actually, that's not what we're looking for. We're looking for the mass of neon to the mass of argon. Okay. All right, there's some assumptions that you have to make here. If you're holding both of those balloons, you have to assume that they're at the same temperature. So this temperature, orange, is equal to this temperature, blue. And you're holding them both together. So I assume that you don't have your hand stuck into a vacuum chamber or a pressure chamber of any kind. So the pressures have to be the same also. Okay? We're told what the volume difference is. Right? So the volume of this one, say, is blue, but the volume of this one is twice the blue. Okay? So what does that mean in terms of what's the fourth factor that defines a gas? Number of moles. So what's the mole relationship between these two? If this one is twice the volume of that one, it has twice the moles. So this has, if this is the number of moles, then not equal to. The number of moles over here is twice the number of moles of that one. Okay, now we can say something, but we don't have all the information we need, do we? We have to use our periodic table. Because how do you get to mass from moles? Molar mass. So what's the molar mass of argon? Well, we looked at it earlier, it's about 40. What's the molar mass of neon? Check it out. It's about 20. Okay. So look what happens. You've got 40 moles of argon at that many moles. And you have, you have 40 grams per mole at this many moles. And you have 20 grams per mole at twice as many moles. So what's the mass relationship? Well, this one went down a half, but it went up twice here. So the ratio is 1 to 1. Does everybody see that? That's so we don't have to do all that math. Well, we sort of had to kick a little bit of math in here, but not much. Okay. Oh, and that means A. A was the answer for this one. Okay, that was 20. Let's see which the next one I have marked. How about 29? A gas sample is heated from -20 to 57. So if we go from this temperature to this temperature, 57, that's a 0 also. Okay. And the volume increases from 2 liters to 4.5 liters. So from that temperature, the volume went from there at 2 liters to there at the new temperature, 4.5 liters. What else? If the initial pressure is 0.14 atmospheres, so the initial pressure, P1, was 0.14 atmospheres. Then it asked us, what's the final pressure? So that means P2. So what kind of problem do we have? A before and after. And we don't just have two factors involved, right? Because this one, volume changed, temperature changed, and pressure changed. So you need the combined gas law, right, which is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, the number of moles stayed the same, right? 29. A gas sample. Okay, so you have to assume that the number of moles stayed the same. That goes out. So now what you have to deal with is these three right there. And P2 would be this one. So if we put P2 on one side and everybody else on the other side, that means P1, V1 is there, plus T2 comes over here. And then on the bottom, we have T1 already, and then V2 comes over on the bottom. Okay? So now, since this is a before and after, oh, what did we not do yet? Temperature. So what's that temperature in Kelvin? Well, 273 minus 20 would be 253, right? 253 Kelvin. And 273 plus this one would be, see if I can do it in my head, 0, 3, 3. Let's see, 2, 6, 10, that's 13, yeah, 330. So those are the values that you have to put in for temperature. The rest of them, as long as the units of measure for the others are the same, you don't have to change them. This could be milliliters. This could be cubic feet. This could be millimeters of mercury. Doesn't matter. Except when you go looking for the answer. So when you go looking for the answer for number 29, it's going to be in atmospheres. So you want to leave that one in atmospheres. And you just plug in the numbers. Now that you've got them set up, put them in their respective places, and you should come up with 0.0811. Atmospheres, which is, for this problem, E. Okay? Let's see. I may have to jump over some that I've collected. Okay, we'll do 30. Then I might have to hopscotch around. A sample of oxygen gas has a volume of 1.72 liters at 27 degrees. Centigrade, and 800 millimeters of mercury. How many oxygen molecules does it contain? That's what we're looking for. This is a state problem. You use the ideal gas equation because you're only given what it is right now. But you have to get your units right. Number of molecules, once you've got moles, that's an easy conversion because all you need is Avogadro's number. So liters is correct. Degree C, need to change that one. So that one looks like 300. 800 millimeters of mercury to give you atmospheres. Okay. And then you solve for moles. So PV equals nRT. Moles would be PV over RT. So the only one we don't have up there is R, right? And it's in useful information. But if you do it enough, you'll remember. Okay, so that plugs in right here. Then you put in this value for pressure, that value for volume, that value for temperature. You find out how many moles you get. So we get our answer in moles, and then we want to convert to numbers. So if that's moles, you need moles to cancel. And that'll give you molecules. Let's see, is that what it's asked for? How many oxygen molecules? Okay, that's important. Why? Because oxygen's diatomic. What if it asked for oxygen atoms? You'd have to multiply that by 2. Right? So that's just the kind of tricky thing that I would do. Just to see if you're paying attention. Oh, and the answer should be A. 4.43 times 10 to the 22nd molecules. Okay. Let's see, I'm still... let's see. The only reason I'm going to be in a hurry is because I don't want to run too far over, because we've got a 2 o'clock, another 2 o'clock meeting. We can do this one quick. 37. Which conditions of P, T, and N, respectively, are most ideal? P, T, and N. What do they need to be for ideal behavior? Pressure, low. Temperature, high. Number of moles, low. With those conditions, you have the kinetic molecular theory of gases satisfied for ideal behavior. Low pressure means there's large volume and just a few molecules, which is the same thing as saying here. High temperature means that they're moving so fast that intermolecular interactions don't have a chance to work. Okay, so that means low, high, low is B, E. Okay. Okay. Jenny Shepard. Must have got kicked off and came back. Let's see. Is Tamara Hunt there? We'll be sure I don't miss anybody. No. Tamara's not there. Okay. So let's see. Move over to how about this one? Interpreting a graph. This one could give some people trouble. (56). All right, so we've got these 4 graphs, and then E is none of these. So let me put the graphs up first. And it's just simply that. That. This. And D. This one. And then E, none. Okay, so what's the question? Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of a different gases at constant volume and temperature? This might take some explanation. I want to be consistent with this explanation. Okay, this is going to require some derivation. I'm sorry, this is going to have some math. So, I'm going to try to squeeze it in here. I took up too much room, actually. So, what are we looking for? Let's go back to the problem. We want the best representation of pressure versus molar mass. So, we would put pressure here, molar mass here. Okay. So what is the relationship between pressure and molar mass? We have to look at what values do we have available. I mean, what relationships do we have? The problem that I solved, the way I solved it before is, I said, what relates all of the values of gas together? The ideal gas equation. And how do we define molar mass or molecular weight? It's mass per mole. Okay? So if we're going to relate pressure and molecular weight, then we need, and the sample is the same. Mass is constant, right? 1 gram. So in order to put them both together and relate pressure and molecular weight, we could use these two equations, and they're related by the number of moles. Right? So if we solve for the number of moles, we have mass divided by molecular weight. Then we can substitute this one in there. So this gives us, I'm going to come over here. This gives us PV equals, number of moles equals mass, molecular weight, RT. Okay. Mass is constant, R is constant, temperature doesn't change, and volume is not changing. So let's put them in a relationship where we have the constant on one side, right? Try to make it look like a gas law. So if we put volume over here and molecular weight over here, then we get MRT over V. Right? Okay. If this is a constant, what does that look like? That times that is a constant is an inverse proportion. It looks like Boyle's law. Well, it has the same form as Boyle's law. That's not volume. But it has the same form as Boyle's law. And what does Boyle's law look like? Looks like a hyperbola, doesn't it? So that means that none of these are accurate. None of them tell us what this relationship is in a graphical form. So that's why E is the answer. None of them work. Did I lose anybody? I think the trick to this problem is assigning these axes and then saying, all right, how do you get to those variables in an equation? Gases are related by this. Molecular weight's a different animal, but they do have something in common, and that's moles. When you have two equations with one variable in common, you can combine them. about to crown one of my cats. Soundly sleeping over here, ready to be crashed. Okay. Let's see. I have 61 marked, but the solution to 61 is also using the combination of the ideal gas equation and molecular weight. And what that gives you is the molar mass for this gas. Yeah. It gives you the molar mass, and then you can relate the molar mass. Yeah, I'm running out of time. So 61, you're going to have to look at that one on your own, but it's worth looking at. Okay. Let me get a couple of these out of the way. They're real quick. 82. What's the standard temperature for a gas? Right, when we say STP, standard temperature and pressure, standard temperature for a gas is 0 degrees centigrade, which would be 273 K. And then the standard pressure, which is 83, is 1 atmosphere. So if a problem ever says gas this and gas that at standard temperature and pressure, if only gases are involved, it's 0 degrees. Later on, when we talk about standard temperature and pressure for other chemical reactions, the standard temperature is 25 degrees. But for gases only, and for this chapter, it's 0 degrees. Okay. Oh, this is a good one. 94. All right. 94. So we're given a diagram here with two bulbs filled with gas at the given information. So let's draw the picture first. So we have and that's a valve. The valve is closed right now. This one is 3 liters. This one is 2 liters. And the pressure in the 2 liters, 1.8 atmospheres. And the pressure in this one is 3 atmospheres. Okay, what's the final pressure? If the temperature remains constant, when you open that valve, what's going to happen? Qualitatively speaking, this gas is going to go over there that way until they're the same pressure all the way through. Right. So let's just say, for argument's sake, we have 2 different gases here, just so we can tell their partial pressures apart. If we there, shut that up. Okay, so let's go back to the question. What's the final pressure? Okay, so what's the final pressure after we open the valve? So that pressure is actually going to be equal to what's the pressure due to this gas on that side, and let's just call this piece of 2 liters plus piece of 3 liters. Now, we can't add them together yet, right? Because they're separate. They're not mixed together, right? So their partial pressures do not satisfy Dalton's law of partial pressures. They have to be mixed first. So the way you do that is you treat it as two separate problems. Assume that this is a vacuum. And then you allow this gas to stream into there until it equilibrates. And that gives you the partial pressure now of that gas. Then you go say, that's a vacuum. And you let this one come over here and equilibrate. That's the partial pressure of this gas. Then you can add them together. So pressure volume, for this one, we've got a starting pressure and a starting volume. And then we're going to have a final pressure, which is our unknown, and then a final volume. So what's the final volume? 5 liters. And that's going to be the same for both of them. The same form. So what you do is you say P1 here is 3 divided by 3 times 5. Right? So 3 into 15 is, well, that doesn't work. Hold on a second. Hold everything. Oh, wrong place. One. I wrote that wrong, and nobody caught me. Right? Nobody caught me. Right? That's the proper Boyle's law. So this overall volume here is going to be 5. That stays the same. This is our unknown, and then we just change these for the 3 times 3. So that's 9 divided by 5. So this one is 9/5 atmosphere. And this one would be 1.8 and 2. So 2 times 1.8 is 3.6 divided by 5. Right? So now we have those are the partial pressures of each one. 9/5 and 3.6/5. Add them together. So we get 12.6/5. So that would be about 2.5 atmospheres. So let's see if we have an answer that fits 2.5. Yeah, 2.52. Okay, did I go too fast? Or does everybody understand? This is a combination of Boyle's law and Dalton's partial pressures. The trick is understanding that in order to have a partial pressure for one gas added to the partial pressure of the other one, you have to treat them as separate Boyle's law problems first. So that means that's a vacuum first, then this is a vacuum second. That gives you the partial pressure of each gas that you can add together. All right, I got 4 minutes left. And that's not all the problems I wanted to work with you. But let me see if there's one last one that is worth looking at. We haven't touched on Graham's law yet. Let's see. Actually, I've got 2 of them, so I'm gonna run over a little bit and do both of these. Shoot, we got 3 that need to be done. Oh well. All right, so if you have 116, if you and a friend are going to make hydrogen chloride by releasing one friend releases hydrogen from this side of the room, and the other one releases chlorine from this side of the room. You want them to meet exactly in the middle, or in the middle position of the room, right, to form your HCl. So who needs to release first? Which one moves faster? Hydrogen moves faster than chlorine, right? Because that's 2 molecular weight, and that's about 70, 71 actually. So if this one's moving slower, that one needs to be released first, which is why the answer is B. Your friend releases the chlorine gas first. Then it will, if you time it right, then they'll meet in the middle. Okay, that was 116. Let's see, the other two. Let's see. 132 uses a term that we haven't discussed yet. It's called a manometer. A manometer is like a barometer, only there's our barometer. A manometer seals this off. And allows you to measure the pressure in that vessel. Right? So instead of atmospheric pressing down, it presses down from the gases in that container, that reaction container. So that's a manometer. So it's attached to a sample of gas that occupies a volume of 2.34 liters. Okay? The mercury level in the arm of the manometer I didn't draw that exactly right, is attached to the gas sample, is 24.3 torr lower than the arm open to the atmosphere. Okay, so we've got that's one way to draw a manometer. Here's the other way. Okay, so mercury's in here, and this is 1 atmosphere. Okay, and the level in the arm of the manometer attached to the gas sample is 24.3 torr lower than the arm in the atmosphere. So down here versus here, is 24.3 torr. So what's a torr? A torr is the same as a millimeter of mercury. Right? So the difference is the pressure inside here is greater than atmospheric by that much. So if you're on the Dead Sea, the atmospheric pressure is 1.23 atmospheres. 1.23 atmospheres. So what's the pressure of that gas? It's 1.23 times 760 plus 24.3. Right. The pressure in here has to oppose atmospheric as well as the weight of the mercury. So the total pressure is whatever's bearing down here plus that. And you'll see that example in Boyle's law when you look at the demo for Boyle's law. In order to determine the pressure on the syringe inside the pressure vessel, you have to add atmospheric to what you measure inside the vessel to get your total. The same idea here. Okay, I got one more. All right, one more, 142. Okay. Consider the reaction between ethane, C2H6, and oxygen. These are both gases. Okay. To produce carbon dioxide and water. CO2 and water. What volume of carbon dioxide will be produced at standard temperature and pressure from the reaction of 4 liters of ethane and 7 liters of oxygen? And let's read the question again. What volume of carbon dioxide? So we've got a gas here, and we're looking for what volume? Okay, this is a stoichiometry problem using gases. First thing you need is a balanced equation. Okay. So can we easily balance that equation? Possibly. Oxygen's here, and it's in 2 places there, so we're going to need our budget. So we've got carbon, hydrogen, oxygen. Starting off with 2 carbons, 6 hydrogens, 2 oxygens. And over here we've got 1, 2, and 3. Okay, so if we say 2 carbons here, that changes this to 2 and this to 5. Hydrogen then, let's say we go 6 here, we need 6 hydrogen here, so we have 3 there. So that makes 6 hydrogen there, but that changes the oxygen to 4 plus 3 is 7. Okay. So we need 7 halves there to give us 7 here. And then overall, we have 2, 7, 4, and 6. Okay, now we've got a balanced equation. We can do our stoichiometry. So if you've got 2 reactants and you're given exact amounts of each one of them is limiting. So we've got to find out which one runs out first. Well, according to the gas laws, standard temperature and pressure, right, those haven't changed, then these are proportional to moles. So you can use them as if they were moles. So if we say all of this is converted to that, the ratio is 4 liters. And then we have 2 C2H6 and 4 CO2, which means we have 8 liters of CO2. But if we do oxygen, we have 7 liters of oxygen, and the conversion here is O2 is 7 to 4. So 7 cancels, and we have 4 liters of CO2. So the limiting is oxygen, and we've solved the problem already. It's 4. That's the least amount. So that's the value for the volume. The key here is to understand that if the temperature and the pressure don't change, then the volume is proportional to the moles. That's Avogadro. So you can use the liters, the volume, directly as if it were moles. And that's why the answer is C. Okay. That's all I got time for, I'm afraid. Well, let me tell you the ones that that I had to skip. Maybe you can take a look at those. We did those. Number 124. Let's see. Take a look at 124. 118, 117. Did that one. What else did I skip? 109. 103. 95. And I think oh, 86. 80. 81. I did skip a lot, didn't I? Those are the ones I wanted to get to. And I believe I talked about 61, but you better look at that one, because I would have worked it exactly the same way as in the review document. I skipped 53 and 52 also. Okay. All right. So that's all we have time for. And I will reconvene at 2 o'clock in 6 minutes. And this is voluntary. This is like we did for the Excel lab where we met Zoom for Excel. This one we're just going to do, this is going to be a problem solving thing. Right, so come with your problems. So, because I don't have anything prepared. And we'll, like I say, this is voluntary. We'll meet again at 2 o'clock if you want to. And we'll talk about labs only. Okay?